Welcome to the first half of section 8.2. We've got a lot to do today, so I'm just going to jump right in. Some of the preliminary material, here I've got a picture from Euler's integral calculus where he uses power series to solve differential equations. That's what we're going to have to do in this chapter, and the reason we're going to have to do that is, for the most part, differential equations with variable coefficients, such as Legendre's equation or Bessel's equation, cannot be solved using variation of parameters and the other methods we've learned so far in this class. They have to be solved using power series. So today's just a review of some things that you may or may not know about power series, but you will know them by the end of today. Some terminology. This is from Calc 2, this graphic, if you remember that. The interval of convergence for a power series is the set of all x for which that power series converges. Now, a typical power series will be centered at a number x naught. Most of our power series today, all of them actually, will be centered at x naught equals 0. So they'll have formulas that look like Cn x to the n, and they'll start maybe at 0, maybe at 1, wherever. And then, again, this is a graphic for how to find the interval of convergence for a power series. We used the ratio test, and the rules for the ratio test were to get absolute convergence, you needed rho less than 1. But I don't think we're going to need that today. So moving on to adding power series. Okay, we can add power series by combining the coefficients, as long as the power series both start in the same place. If they don't, I'll show you what to do. So for this first example, we have two power series. They both start at 0, and we want to find a single power series for the sum. So in this expression above, this would be my an, the 1/4 c to the n, and then the ncn would be my bn. And so to add f and g, I just combine the coefficients. The sum, n equals 0 to infinity, of parentheses 1/4 cn plus ncn, and then a single x to the n. And then if there's a common coefficients, like if this is a cn and that's a cn, you want to pull that out so there's only one occurrence. So this will be sum, n goes from 0 to infinity, of 1/4 plus n cn x to the n. Okay. Let's do another one. Write down a power series, single power series, for the sum of f plus g. And here we see that f starts at 0, but g starts at 1. So when that happens and we want to combine, we need to combine both power series, and they will start at the highest value of these two power series. So this one starts at n equal 1. When we combine, we're going to have to start them both at 1. So what we need to do is rewrite f like this. We want it to start at 1. Okay, so we'll just start it at 1. N equal 1 to infinity of 3cn x to the n. But I took off the 0 term. So when n is 0, I'll just put that term over here, 3c naught. Now I've got all the terms. Here's the n equals 0 term, and here is the n equal 1 to infinity terms. So now I can add f plus g. F is 3c naught plus the sum, n equals 1 to infinity of 3cn x to the n. And then I'm adding g, which is 1 to infinity ncn x to the n. And so when I add, I get 3c naught plus a single summation sign, n equals 1 to infinity of, I'm going to add the coefficients. I've got 3cn plus ncn, so that's 3 plus n Cn, and then a single x to the n. Okay. Now remember, you can slow me down if you have to, but I'm going to go through this fairly quickly because I've been doing it for a while, and once you get good at it, you'll be doing it this quickly too. Okay, so let's do another one. Well, actually, why don't we pause and practice? So why don't you try this one? Write down a power series for the sum f plus g. Okay, so g starts at 2, so we need to start f at 2. When n is 0, 0 factorial is 1. So I get c naught, this is the n equals 0 term. And then when n is 1, I get 1 factorial, which is 1, just c1x. By the way, when n is 0, I have x to the 0, which is 1. So just c naught, and then c1x, that's n equal 1. And then continue on, n equals 2 to infinity, n factorial cn x to the n. So now when I add f and g, I'm going to take these two pieces of f, c naught plus c1x plus, now I'm going to add f and g in my head. So n, well actually not in my head, on the paper, n equal 2 to infinity. I'm going to combine the coefficients here. I've got 4cn and I've got n factorial cn. So that's going to give me n factorial plus 4 cn and then x to the n. And so typically when you're adding power series and you're solving differential equations, what you're going to have to do is reindex, which we'll talk about in a minute, cull some terms off. That's what this is called. I'm culling off 2 terms so that I can combine both of these, because you can only combine when they start in the same place. You can't add an n equal 2 to an n equal 0. You can only add an n equal 2 to an n equal 2. Okay, something that we'll come back to in section 8.3, but I just want to mention it now. Setting power series equal to 0. If a polynomial is 0 for all x, that means all the coefficients are going to be 0. The same is true for a power series. So if you have a power series that's identically equal to 0 for all x, that means all the coefficients have to be 0. So, for example, we might be solving in 8.3, we might come down to a final equation that looks something like this, and we might be solving this. So what would that mean in terms of our c's? Well, this is the constant coefficient. That's going to be 0. So I'll call this equation 1. Equation 2 is that the coefficient of the x term has to be 0. C1 plus 1 has to be 0. And then equation 3 would be all the other coefficients have to be 0. So n plus 1 minus cn has to be 0, and that's for n equal 2 to infinity. So I'll have 3 equations. Let's clean these up. The first one doesn't need much cleaning. The second one is c1 is -1. And the third one, typically we'll want to solve for the higher index, cn plus 1 is cn over n for n equal 2, 3, ... And these are called the recurrence relations. These are called the recurrence relations. And we'll talk about those again when we start solving differential equations. So, reindexing. This is something we did a lot when we found the sum of a geometric series. So you may or may not remember this. If you don't, it's okay. It's pretty easy to do. When you reindex, whatever you have to do here in the formula, you're going to do the opposite to the index, and vice versa. Whatever you have to do here, you'll do the opposite in the formula. So for example, if I want to take this power series, which is written in n plus 1, and reindex it so it's a power series in x to the n, that means that up here I'm going to need to subtract 1 from the exponent. So everywhere in this formula, I'm going to subtract 1 from n. That means that down here, I'm going to add 1. All right, so my power series is going to start at 1. And then everywhere I see an n, I replace it with an n minus 1. That includes the cn. Let me erase this so you can see it again. The cn becomes c sub n minus 1. And then n plus 1 squared, if we replace n with n minus 1, we just get n squared. And then x to the n. So now I have a power series in x to the n. Now, suppose I want to write that starting at n equals 3. So this would be common. We'll have to rewrite this so it starts in a certain place. If I'm starting at 1 here, if I want to start at 3, I'll just go ahead and do that. Leave some space. N equals 3 to infinity. Cn minus 1 n squared x to the n. And then we've left off the n equal 1 and n equal 2 terms. So we'll put those, n equal 1, n equal 2, we'll just write those down by hand. So when n is 1, I get c naught times 1 squared times x. So I get c naught x. And then when n is 2, I'm going to get 4c1 x squared. So you don't have to write down underneath what value of n you're using. I'm just doing that so you can see where these terms are coming from. So now I've written that as a power series that starts at 3 by literally pulling off the first 2 terms by hand. Okay, so now we're going to do some examples, and we're going to do 2 things for each example. By the way, your homework is going to have you switch from an n to a k, but I don't see any reason to do that, and you'll see what I mean when you get there. Okay, we're going to do 2 things for each power series. We're going to reindex so all the reindex so the series starts in x to the n, and then we're going to combine. If there are two power series or more, we'll combine them to write as a single power series. So for the first one, we need to reindex it. So this one's the exponent of x is n minus 2. We want that to be n. So that means everywhere in the formula where I see an n, I'm going to add 2. That means down here, I'm going to subtract 2. So this guy's going to start at 0. And then everywhere in the formula where you see an n, just put an n plus 2. N plus 2. N plus 1 becomes n plus 3. N becomes n plus, what am I doing? I'm adding 2. N plus 2 quantity squared. 1 just sits there. Cn becomes Cn plus 2. And then x to the n minus 2 becomes x to the n. And we're done. Step 2, rewrite as a single power series. Well, that's not applicable because there's only one power series to begin with. So we only have to do one thing there. Okay, next one, we're going to have to, 1, reindex. No, we don't, because already these guys start, these guys are already written in x to the n. So number 1's NA. Number 2, we want to combine. So this one starts at 2, this one starts at 0. I need to start them both at 2 because the higher value of 0 and 2 is 2. So that means I need to write this one as, we need to pull off the first 2 terms by hand. So that gives me C naught plus C1x plus sum n equals 2 to infinity of Cn x to the n. And then the next power series, I'm just going to copy it down. 2 to infinity NCN x to the n. And now I can combine C0 plus C1x plus a single summation sign, n equals 2 to infinity of, I'm going to add the coefficient Cn plus NCN is 1 plus n Cn x to the n. Okay. So the first one, I only had to reindex. I didn't have to combine. The second one, I didn't have to reindex. I only had to combine. Now you can guess I'm going to do both. I'm going to have to reindex and combine. So step one, this guy needs to be written in x to the n. So I'm going to add 1 in the formula. I'm going to subtract 1 at the base. So n equals 0 to infinity. And then everywhere I see an n, I'm going to replace it with an n plus 1. N plus 1, Cn plus 1, x to the n. And then this second guy, need to add 2, so I'm going to subtract 2. So this one will start at 1. It'll go n plus 2, n plus 1, Cn plus 2, x to the n. Okay, step 2. This one starts at 1, this one starts at 0. To add them, I need to start them both at 1. So that means I have to cull off the 0 term of this first power series. So when n is 0, I get C1 plus n equal 1 to infinity, n plus 1, Cn plus 1, x to the n. I'm just copying things down now. N equals 1 to infinity, n plus 2, n plus 1, Cn plus 2, x to the n. All right, and now I'm ready to combine as a single power series. This is C1 plus big old summation sign, n equal 1 to infinity. And looking ahead, this is Cn plus 1, this is Cn plus 2. I won't be able to combine those like I did in the previous problem where I had NCN and a Cn. Those both had Cn in them. I could factor the Cn out. I can't do that here, so I'm going to have a big bracket, and I'm just going to write down the coefficients. N plus 1, Cn plus 1, plus the coefficient over here is n plus 2, n plus 1, Cn plus 2, close bracket, x to the n. Today, this is all we're doing. Pretty soon, we'll be setting this equal to 0, writing down recurrence relations, and solving for the c's. Okay, one more I'll do with you. Again, this one's going to need a couple of things done. So the first thing we have to do is reindex the middle term. So the first term stays put, n equal 2 to infinity, and you're going to have to write small, n minus 1, Cn x to the n, and then plus, I'm going to do two things. I'm going to reindex, so this is x to the n, and I'm going to bring the 2 inside. So I'm going to add 2 in the formula. That means this guy's going to start at 0. I'm going to bring that 2 in and replace n with n plus 2. So n plus 2, n plus 1, Cn plus 2, x to the n. And then for the third power series, I don't need to do anything but bring that 3 in. I don't have to reindex. So this one starts at 1, 3n, Cn, x to the n. Okay, now this one starts at 2, this one starts at 0, this one starts at 1. I need to start them all at 2. So I'm going to have to cull some terms off of the second guy and the third guy. So the first guy, not going to do anything there. n equals 2 to infinity of n minus 1 Cn x to the n. Second guy, I'm going to pull off the first two terms. So when n is 0, I get, let's see, 4c2 x to the 0 is just 4c2. And then when n is 1, I'm going to get 12c3 times x. And then I'll finish off n equals 2 to infinity of 2 n plus 2 n plus 1 Cn plus 2 x to the n. All right, now we're ready for the third guy. We need to start this guy at n equals 2, so we have to pull off the n equals 1 term. So that gives me 3c1x. And I add n equal 2 to infinity 3n Cn x to the n. All right. Now I'm ready to combine. So I'm going to pull off my the terms first that aren't attached to a summation sign. So I'm going to have 4c2, bring that down. And then for the coefficient of x, I've got 12c3 and 3c1. So parentheses 12c3 plus 3c1 all times x. Then single summation starting at 2. And let's see what we have here. Big bracket. I'm going to have some n plus 2s, Cn plus 2, and then I'm going to have some coefficients involving Cn. So looking at this first and last power series, I see I have a 3n Cn, but I also have an n times n minus 1 Cn. So I did my scrap work down here. The coefficient of Cn will be n times n minus 1 plus 3n. Simplified that to n squared plus 2n. So n squared plus 2n Cn plus, then I'm going to write down this coefficient, 2 n plus 2 n plus 1 Cn plus 2. Then I close my bracket. All of that is times x to the n. And that's it. So when I combined, just let's go backwards here. When I combined, I didn't want to write down just, okay, so this term's fine, but I didn't want to just copy down n times n minus 1 Cn plus 3n Cn plus n plus 2 n plus 1 Cn plus 2 x to the n. That would be kind of sloppy. I'd have a Cn and another Cn. And when we actually start solving differential equations, we'd have to combine that into a single Cn. And so that's what I did here. So that I have a single Cn, and then there was only one Cn plus 2 anyway. So that's as good as you can get it, given that we're not going to do anything else to that power series. All right, you've got a couple there for practice, and that is the end of part 1 of section 8.2.